So we're going to start a new topic here, which is the method of cylindrical shells. So in the video we just did, we ended up with a kind of bundt cake, solid. So you're going to get that whenever you have something kind of like this. And now let's rotate this around the y-axis. And let me shade the plane region just so you know what's doing the rotating. So that's going to make a bundt cake, and it looks kind of like this, and then inside it looks sort of like this. So all these lines sort of go down to the bottom of the thing. Okay, so it looks like that. And last time when we did this problem, we integrated with respect to y. So we were given this curve, y equals f of x. And so we were able to solve x equals f inverse of y. But that won't always be possible. So, sometimes you can't always solve every equation. Like an example is a fifth degree polynomial. So if I wrote y equals a plus bx plus cx squared plus dx cubed plus ex to the fourth plus gx to the fifth. So here's a degree 5 polynomial. It's just not possible to solve this equation for x. And so that means that you can't do this trick that we did last time and just use the inverse function, because you can't really compute the inverse. So it turns out that there's a method that is really well suited to doing this kind of problem. It's called the method of cylindrical shells. And the idea is like this. Let me pick a color that will stand out. So it starts with a partition. We're pretty familiar with that. So you partition this space into, so here, let's pay attention to these two. So here's xi minus 1, and here's xi. And these are just the standard things that we always use, like a is x0, and then xi is I times delta x plus a, etc., etc., etc. We've done this many times. So now let's stand up a rectangle here. Write it kind of like this. The height of this rectangle is going to be the midpoint of this interval. So I use the midpoint to determine the height of that rectangle, and now I spin the rectangle around. So what does that do? That makes a cylindrical shell. So this is where the name of the technique comes from. So here's a cylindrical shell. And drawing is not so great. So like this, it's hollow on the inside. So it's kind of like a combo, but without any stuffing, without any filler. Okay, so it's hollow straight through. That's the shape that it makes. And so the strategy here is to figure out the volume of this cylindrical shell, and then use the sum of all the shells to approximate the volume of the solid. So this is also a trick we've done a few times before. So let's figure out how to find the volume of this cylindrical shell. It's really just a generalized cylinder, and look at the this is going to be delta x. That's because that width is xi minus 1. But let's use the general cylinder formula here. So if I cut what we need to know is the area of the base of the area of the base. So the area of the base is going to be, what does the base look like? The base looks like an annulus, and it has an outer circle and an inner circle. I'm sorry, those are terrible circles. So this annulus has area equal to pi xi squared minus pi xi minus 1 squared. Okay, and so that means that the volume of the shell is going to be the area of the base times the height. What is the height? The height is f of the average of these two. So here, let me write all that out. So let's call xi star the average of xi and xi minus 1 divided by 2. Okay. So that's the midpoint of the rectangle. Hope everybody can see that. We're talking about the line right in the middle of the rectangle. So the place where it touches the x-axis is the average of these two, which we're calling xi bar. And so the height of the rectangle is f of xi bar, so that becomes the height of the cylinder. Okay, and so now we'll use the formula for the volume of a cylinder, which is the area of the base times the height. And so what is that? The area of the base we just computed. It's pi times xi squared minus xi minus 1 squared. And times this, we multiply the height, which is f of xi bar. Okay, and now I'm just going to chop this up and there are a couple neat things that happen. So first, let's apply the difference of squares formula. So by the difference of squares formula, this is the same thing as xi minus xi minus 1 times xi plus xi minus 1 times f of xi bar. And now look at the neat things that happen here. One thing that happens is that this is just delta x, because all the partition points are separated by delta x. Another neat thing that happens here is that this is 2 times xi bar. Isn't that funny? Because here's this. So 2 times xi bar is equal to that. All right, so we make those changes, and we get for the volume of the ith cylinder is equal to pi times delta x times 2 xi bar times f of xi bar. Okay, now I'm going to need some more paper. Let's go to the next page. I'm going to take that with me though. Let's copy this and go to the next page. Alright, so this is the volume of one of those cylinders. Okay, and what are the cylinders? We're sort of approximating this thing by chunky cylinders. So it's approximately going to be like, instead of that smooth bundt cake, we get sort of this like angular bundt cake from rotating these sharp-edged cylinders around. But as the cylinders get smaller, as the width of each of the cylindrical shells goes to 0, this approximation becomes perfect. So the volume of the whole thing is approximately equal to the sum of the volume of all the cylinders, which is 2 pi delta x I bar says I goes from 1 to n. And so now we do the calculus trick. So this will be exactly equal in the limit as the width of the shells goes to 0. So I'll make the number of shells go to infinity. They're all equally spaced, so that makes their width go to 0. And we get this. And surprise, 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 this turns out to be an integral. This is the integral 2 pi delta x f of x dx. And there's no delta x. Yeah, oops, that was dumb. And let me move this over like this. Okay. All right, so now we have an integral for finding the volume of this solid, and we have to integrate over each shell. So you integrate over just this. So if this is 4, then it's the integral from 0 to 4. But we'll just write a to b here. But you should make these limits so that the x ranges over all the shells. Okay, cool. So now let's use it to solve some problems. One thing that's kind of new is we haven't been able to find the volume of a sphere yet. Let's find the volume of a sphere. We could do it for a general sphere, but just the first time that we do this, let's not break anybody's mind. So, you know, you can describe the top half of the unit sphere as y equals the square root of 1 minus x squared. What we're going to do is we're going to find out the volume of the unit sphere. So that's the sphere of radius 1. So how can we do that? We can take this and rotate it around here, and that will make the upper hemisphere. So we rotate this plane region around the y-axis, and it makes the upper hemisphere, and then we'll just double that to get the volume of the whole sphere. And if we were doing this to prove the formula, then you just change this to r squared instead of 1. So if you want to find the volume of a sphere as a function of the radius, then you can just redo this problem using r squared instead of 1 right there. Okay, so let's do it. We want 2 times the integral from 0 to 1 of 2 pi x times the square root of 1 minus x squared dx, which turns out to be a nice little substitution problem. So let's do u equals 1 minus x squared, then du equals minus 2x dx, minus 1/2 du is equal to x dx. And so what have we got now? This minus 1/2, let's say that it hits that and just makes it minus 1. So you get, and I'm going to call this guy cancelled now. He died when he hit this thing and made -1. And how did the limits change? 0 gets plugged in and becomes a 1. 1 gets plugged in and becomes a 0. And so you still have the 2 pi. But now it's the integral of the square root of u du. So this is 2 pi times the integral from 0 to 1 of u to the 1/2 du. So this is u to the 3/2 divided by 3/2. Man, it's annoying. That's copyrighted material, yo. Okay. So 2 times pi, and then we go from 0 to 1. So this is 2 pi times 2/3, which is 4/3 pi. Awesome. So that's probably right, because we know that the formula for the volume of a sphere is 4/3 pi r cubed. So if r is equal to 1, that's what the answer should be. Okay. So we seem to have done that one correctly. What about, let's take, I've always liked this function. This function is a little bit mysterious to me because, for one thing, it's the derivative of an inverse trig function. So it looks like this. This is y equals 1 over 1 plus x squared. And so I don't know too much about complex analysis, but evidently if you graph the same function and where x is allowed to take on complex values, then it has a singularity, which means that, oh, look, if you plug in I into this thing, you divide by 0. So if you look at this thing in the complex numbers, it's very weird, but in the real numbers, it's very tame. So we'll take this region, and then we will rotate it around the y-axis, and let's try to find the volume of the solid. Okay, using cylindrical shells. So we know that we've got to integrate from 0. We've got to decide what this is. What do you want to use? 3? So let's do the integral from 0 to 3 of 2 pi x 1 over 1 plus x squared dx. And this is a nice little substitution problem where you do u equals 1 plus x squared, and then du is equal to 2x dx. 1/2 du is equal to x dx. And let's change the limits as we go along. Put in 0, and it becomes 1. Put in 3, and it becomes 5. Oh, that's annoying. I might prefer to go back to the original limits because there was a 0 there. I really like zeros. So let's just put off changing the limits, and we get 2 pi, and then there's a 1/2 here. So let's just say that that 1/2 kills that 2. So you've got a pi, and then it just becomes 1 over u, right? Oh, you know what? This is, I am going to change the limits because this is going to involve natural log, and natural log turns 1 into a 0. So from 1 to 5. And is this it? There's du. So this is pi times natural log of the absolute value of u from 1 to 5, which is pi times natural log of 5. Interesting. All right. So should we do one more cylindrical shell? Okay. Yeah, I'm looking at one that doesn't lead to an integral that we can evaluate. When you use this method in the cases where you really need it, you haven't really needed it in these examples, but like in the cases where you really need it, I'll give you an example, kind of. Let's say that we wanted to spin the first part of sine. Let's say the y equals sine, and we spun this around. There's really no good way to do this using the methods that we knew before cylindrical shells. I mean, we can use arc sine for this part, but then what do you use to get this big radius? It's just annoying. So it's nice to know that you could do this just by integrating from 0 to pi 2 pi x sine x dx. The only problem is that we don't know how to do this integral. you can do this integral using a method called integration by parts. And you can skip ahead and learn how to do that if you want to. You could just go watch the Khan Academy video, and then you would be able to do that, but we can't yet. But a lot of the cases where you really want to use cylindrical shells, it ends up leading to an integral that you can only solve using integration by parts. Okay, so I'm going to do the torus, and I said that in these videos I would put in something that I would give you some instructions, and if you follow those instructions you could get some bonus points on the exam. So this is a torus. So I'll tell you what, at the beginning of class, the next time we meet, if you hand in a piece of paper, just tear out a piece of paper from your notebook, and on this piece of paper write your name. Don't write name literally, but rather write your own name, and then say promo code equals torus. So just hand that in at the beginning of class on Tuesday, and I will give you 2 points on the exam. And that's to reward people that are actually watching this video. So don't tell your friends. Make them watch the video too. Okay, so promo code Torus. And you can only do that at the beginning of class on Tuesday. Okay. So I love the torus because I associate the torus with graduate school. This is a simple but not too simple shape, and it takes some fairly sophisticated methods to understand what's going on with the torus. Where the torus comes from is from rotating a circle around a line, and it makes something that's technically known as a donut. And that's where we get the vernacular word donut, which refers to a popular pastry. So if you take a circle and you rotate, let's say that we drew a circle out here and we rotated it around the y-axis, then we would get a torus. It would make a donut shape. There's a few choices that you get to make. You get to choose what the big radius is, and then you also get to choose the radius inside the tube. And once you do those two things, then the torus is done. So there should be a formula for the volume of a torus that just depends on big R and little r, and there is. And you can use calculus to figure it out. But we won't figure out the general formula. We'll just find the volume of a torus. And it's always nice to be able to cheat and know the answer beforehand. So if you slice this thing, then you can unroll it like as if it were made out of dough. You can unroll it into a cylinder. And you can use the cylinder, so the volume of the torus will be the same as the straightened out cylinder. It's an example of something called Cavaliere's principle that we've talked about in class before. So you know a formula. This is kind of a Dr. Seuss cylinder, but you know a formula for finding the volume of a cylinder. And the height here is going to be the circumference of this inner part. It's going to be the circumference of this inner circle. And this radius is going to be the inner radius. So you could use that to cheat and find out the answer before you even start, which is what I've already done, so I'm not going to do it now. And that way I can be certain that the answer that I tell you is right. Okay, so this is from the book. So we take, let's put some axes down. And the book takes a circle with a certain radius, which is a radius of 2. They could have chosen something else, but they chose 2. They chose a circle of radius 2. And they rotated around the line We rotate it around the line x equals 4. And that makes a torus. So we're going to figure out this problem using the method of cylindrical shells. So what is a shell going to do in this case? Man, I wish I could draw a straight line. Let's just draw one little shell here. So here's a shell. And when we rotate it around this line, it's going to make a big cylindrical shell like this. So that formula that we've been using is not exactly going to work in this case. That's because we have to think about it a little bit. So when we wrote down the integral of 2 pi x, f of x, we have to remember what these things were representing. This x is basically representing the radius of the cylinder. And this is basically representing the height of the cylinder. So now if I were to use the standard formula, this x here would not be the radius of this cylinder. The radius of this cylinder is actually 4 minus x. So I have to adjust the formula for that reason. But once you do, then it's pretty straightforward. Your integral is going to be 2 pi. 4 minus x will be the radius of the cylinder, and f of x will still be the height of the cylinder. What should we use for f of x? Well, this is the semicircle function, and it has radius 2. So the curve that describes that is the square root of 4 minus x squared and dx. And now let's think about what the limits of integration should be. And I'll be honest with you, I messed this up the first time I tried it, and I got really confused because I thought that I could integrate from here to here and then just multiply that by 4, because you see how this will be like the top quarter of the bagel, and so you should be able to just multiply the top quarter by 4 to get the total volume. That doesn't work, and why is that? It's because this part actually sweeps out more area than the other part because the radius that it swings around is bigger. So this part leads to more volume than the green part. So that method of multiplying this by 4 does not work. But we can just do the top half and multiply that by 2, because that will be exactly the same as the volume created by spinning the bottom around. So we'll go from minus 2 to positive 2 and then double it. Where's my cursor? There it is. Minus 2 to positive 2, and then we'll double that. And so this is kind of an interesting integral. Let's see what happens. It's not that hard at all. I'm glad I found this way of doing this problem, because I always like to do the torus, but sometimes the torus seems too hard. This is a nice, easy way to do it. So we go from negative 2 to 2, 2 pi times 4 times the square root of 4 minus x squared dx minus 2 times the integral from negative 2 to 2 of 2 pi square root, 2 pi x square root of 4 minus x squared dx. Okay, so what did I just do? I just broke this integral into 2 parts by sort of like multiplying everything n to these, okay? So the 4 made this integral, and the x made this other integral. Okay, so now let me save you a lot of trouble here. Remember the definition of an odd function? An odd function is a function such that this is true. So observe that this function is odd. And also it's being integrated symmetrically across the y-axis. But because it's an odd function, it's going to look like this. And this part is going to exactly cancel out that part. So whenever you're integrating an odd function symmetrically across the y-axis, you know that the answer is 0. So that saves us a lot of work. And so now what do we do with this part? This is equal to 4 pi, the integral from -2 to +2. Oh wait, it's not 4 pi, it's 16 pi. 2 times 2 is 4, times 4 is 16. And that leaves this 4 minus x squared dx. So if you're going to actually evaluate this integral, it's not that easy. It requires a method that we haven't learned called trigonometric substitution. But we can just do it geometrically, because what is this talking about? It's talking about the upper part of a circle of radius 2. So I know just from basic geometry that pi times 4 is the area of the whole circle of radius 2. And then I'll divide it by 2 because this is just the upper semicircle. So the answer to the whole thing is 16 pi times 2 pi, which is 32 pi. And I've checked that that's correct. So that's an example of using, this is pretty awesome, isn't it? Like, we found the volume of a torus using calculus. That's like getting pretty sophisticated. So I'm going to stop there, and you need to do a lot more practice on your own, but that's the end.